All right. Okay, if you've got your Chromebook open, go ahead and close it. Just so you know, I'm going to, while you're working in a few minutes, I'm going to adjust this because I don't think you're actually going to get this done. So I'll change that so that you have some time to work on it on Thursday. But I do want to go through some stuff here real quick. And my part of this is going to be relatively limited. What I want to introduce you to is the idea of motion in 2 dimensions. And basically, what we're going to do is we're going to think about objects that are moving in 2 or even 3 dimensions as 3 separate kinds of motion. A 1-dimensional motion along one axis, 1-dimensional motion along another axis at a 90-degree angle to that one, and if it's moving in 3 dimensions, 1-dimensional motion at a 3rd axis at a 90-degree angle to both of those 2. And all of that relies on a, just sort of astounding fact about the way things move, which is that if you know enough about how an object is moving in 1 dimension, you don't need to know anything about its motion in different dimensions to be able to analyze its motion along that 1 dimension. What we say is that motion at 90-degree angle dimensions is independent. And then mathematically, in order to be able to deal with that, we have to look at an object's motion and be able to say some part of that motion is this way and some part of that motion is this way. We have to be able to take apart the motion of an object so that instead of 1 2-dimensional description, we have 2 1-dimensional descriptions. And then we have to put those back together at the end. So we're going to be working with vector quantities and vector components, but we'll hit most of that math on Thursday, not today. So when we look at 2-dimensional motion, and that's mostly what we're going to focus on. Occasionally we'll look at things in 3 dimensions, but mostly it's going to be 2 dimensions. In 2-dimensional motion, we're thinking about how an object moves maybe up and down and left and right, or maybe toward and away from you and left and right, or maybe on some other plane. The plane of motion can be anything. Typically, we're going to be either dealing with a plane that looks like this, where we have objects that are going to be moving up and down and left and right, or it'll be a plane that looks like this, where we have objects that are moving north and south and east and west, so to speak, like a piece of paper flat on your desk. That's not the only kind of 2-dimensional motion we could look at, but those are the most common kinds. We always want the axes of interest to be at 90-degree angles, because when our motion is at 90-degree angles on 2 different axes, then it is independent. And what that means is that we can use our kinematics equations to deal with the motion completely separately. If we know enough about how an object moves, if, for example, we were to kick a soccer ball, up in the air, and then it comes back down to the ground, if we knew enough about how that object was moving, we would be able to look at its left and right motion using our kinematic equations and its up and down motion using our kinematic equations completely separately. As time goes by, that ball is going to go up and then come back down. As time goes by, that ball is going to move to the right, and it's going to do so in predictable ways. This is going to be not the only kind of motion that we look at, but this is what we call projectile motion. When there's something in the air that's not just going straight up and straight down, but it's going left and right as well. It'll follow this curved path. This curved path is a parabola. This graph is not a position versus time graph, though. This graph is a x position versus y position graph. And that can be a little confusing. The parabola that this forms is going to be a parabola where y, the vertical position, is a function of x, the horizontal position. When we look at our motion one-dimensionally, we're going to look at its horizontal position as a function of time separately from its vertical position as a function of time. When we're dealing with quantities that have 2 or 3 dimensions, then we need to know more than what we've already known. We've been using vector quantities already. Velocity, acceleration, position, displacement, those are all vector quantities. But we've just been saying it's either plus or minus. We have something different to think about now, because we can have a positive or a negative vector quantity in our x dimension, positive or negative quantity in our y dimension. And when we look at the overall motion, we can have objects that are moving at an angle to both axes. It's not positive or negative anymore. It's associated with maybe like an angle in degrees. And those kinds of quantities, which we've already been using, but only one-dimensionally, when we're using 2-dimensional vectors, we add a layer of mathematical stuff that we need to think about. Yeah?
If you were comparing this, like the up and down position versus the, like, for example, if you're like throwing like a baseball or something, like if you have that graph compared to the height versus the time graph, would it kind of just be like a weird, like, stretched out version of it or something?
Yeah, well, yes, because it depends on the scale of time. Like you could, if I plotted the y versus t, and I set it up so that my initial time was physically located here, and my final time on the graph was physically located here, then the y versus t and the y versus x graphs would look exactly the same. They would look the same, but they're not showing the same information. Yeah, but that's a good point. Okay, so there's a bunch of YouTube videos here. This is what I'm going to show you right now. And they're short and very interesting and kind of fun because this really gets at the nature of this independence in 2 dimensions, all right? So for this first one, what we're going to see is, and I used to have one of these, and it bugs me that I lost it, but I lost it. This is a device that drops 2 ball bearings at the same time. One of them, it pushes it this way as it falls, and one of them, it just drops it. And what you'll see is that the one that's moving horizontally has the same vertical motion as the one that's moving purely vertically, right? So, and it plays it in slow motion. So you'll see the fast motion version of it. No, it's still going, okay. Oh, that's just the slow motion version. Okay, so look, you can see these two, they're hitting the ground at the same time. They're bouncing to the same height. And the fact that one of them is also moving to our right has no impact on where it's located vertically. They both are moving with the exact same vertical motion. All right, so that's one example of the independence of motion at 90 degrees. Here's another example. This is not it. This is beautiful drone photography, but not what we're interested in. So this one is going to show a ball, and it's really funny. I know I didn't make this. I don't know where this came from, but when I first found it, I realized these are the exact same tiles that we have, like the very same ones. So it could just as well have been me, but it wasn't. So what's going to happen here is the ball is rolling this way, and then it's going to get hit by something, but it's going to get hit at a 90-degree angle to its motion. And what you're going to see is that it adds some vertical, not vertical, but some like this way motion without changing the horizontal motion at all. And this is the one where it's going to do it a couple of times, and it's going to show you little grid marks that match up with the location on a frame-by-frame basis. So see these grid marks? You can see how far apart they are. So this is how far it moves in each frame, left to right. And then when it gets bonked, we'll see that it not only has this left to right motion, but now it's moving up and down on the screen as well. But look, the left to right motion is the same as it was before. We've added some new motion in the up and down direction, but we haven't changed anything about its left to right motion. All right, and then this one, there's sound on this one, and we gotta listen to it. This one is so great. The backstory here is that for a whole variety of reasons, a lot of like physics professors have an accent. It's not unusual. So when I was in college, this wasn't my professor, but I had a professor who was Russian, and so this like just reminds me so much of my college years. And this apparatus that he has, we could probably buy this or make it, but like this is what, we used to have money for stuff like this in schools in the good old days. You'd go and you'd be like, I have this one demonstration that I want to do, and I need to spend $1,000 to get it. And people would be like, okay, and then we get it. And now, of course, we don't have that kind of money, so instead of me doing the demonstration, you get to watch him do it. But it's still worth it because the way he talks is awesome. Like, you're gonna love just listening to him talk.
So here's the golf ball. I'm going to fire the gun now. Close. Close. Reasonably close. Well, since it's only reasonably close, perhaps it would help if we give it a little bit of leeway. There goes the gun. Here comes the ball. And this is just in case. Take it down. So as I'm going to push this now, give it a push. The gun will be triggered when the middle of the car is here. You've seen how high that ball goes, so that ball will go. And depending upon how hard I push it, they may meet here or they may meet there. You ready for this? You ready? I'm ready. Physics works.
Nifty, huh? So, again, what we're seeing there is that as that ball gets started moving left to right from our vantage point, the fact that it's also kicked up at a 90-degree angle doesn't change its left to right motion at all. So while it's going up into the air and back down, it's still moving left to right at the same speed as the car. All right, these last examples, these were college students. This is not something that you are allowed to even think about doing, but somebody else did it, and so we're going to take advantage of their work. Just recognize that this is actually not safe, and so don't do this. All right. So, I'm not going to show all of these, but there's a couple of really cool things that you can see from the way that they edit it. So, they have some different objects. They're in the back of a truck, and they throw the objects up in the air. So this is the same thing that we just saw, right? It's just instead of a cart and a little ball on a track, it's a person in a truck. But here's what's really cool is if we isolate and just look at the ball, we see this parabolic curve. So this is what I mentioned earlier. It's called projectile motion. This is what happens when you have an object that's moving horizontally while it's in free fall. But if we then edit the video so that it looks like the ball is staying in the same place horizontally, you can see it goes up and it comes back down. It's almost exactly as if the truck wasn't moving at all. Not exactly. And the reason it's not exactly is because there is some air resistance, and the truck is probably not going at a perfectly constant speed. And maybe he didn't throw it at perfectly straight up relative to himself. All right, so all of those are examples of this idea of independent motion in 2 dimensions. So where that leads us is to, hang on, let me get this set up right. I'm probably going to need me to some adjustments because it always seems to. Okay, so what that leads to is an idea that if we just know that acceleration is constant and we know some of the parameters in each of our 2 dimensions, we should be able to do a lot of predictions for 2-dimensional motion. Specifically, we're going to start with this idea of projectile motion. And what we need to know in order to make predictions of projectile motion is enough information so that we can use our equations to solve for something that we don't know. It's not always the exact same thing that we're looking for. Sometimes we know how fast an object is going in the direction of its travel at the end of its motion. Sometimes we know how long it's been in the air. But in a very general sense, typically what we're going to try to do to start with is we're going to try to predict how far something is going to go horizontally if we know something about its motion at the start. Okay, so there's a lot of different predictions that we can make, but the simplest one is to predict the horizontal displacement of an object. How far will it move horizontally while it's in the air? It's in free fall. There's nothing holding it up there's nothing holding it up, and there's nothing causing it to change its motion except the Earth's gravity. So what that means is if we know how fast it's going, the angle of its launch, and how high off the ground it was launched, then we can predict the path that it's going to take. Its horizontal acceleration should be basically 0. Why? Because objects in free fall have acceleration straight toward the ground at about 10 meters per second squared. It doesn't matter if they're moving left to right, their acceleration is in the same direction. So they have a vertical acceleration of 10 meters per second squared in this direction and a horizontal acceleration of nothing. So here's the, basically I'm gonna just show you a couple of quick things, and then you're gonna have a chance to get started with some work. Here is what it looks like if we launch something at a horizontal angle. So if we know how fast it's going, we know how high up above the ground it is, and it's launched at a horizontal angle, then it's going to go the same distance and follow the same path every time. If we lower it, we can predict what's going to happen. It's not going to go as far. If we increase its speed, we can also predict what's going to happen. It'll go farther. So a horizontal launch, the only things we need to know are how fast it's coming out of the projectile launcher and how high up above the ground it is. That won't cut it when we start looking at angles, because now we can change the object's launch angle, and that will change the position or the horizontal displacement. So let me clear this so that we can see this a little bit better. So I'm going to slow it down a little bit, and at 5 meters off the ground, you'll see that at different angles, we're going to get different distances. So it's all the same speed, it's all the same height, but different distances depending on what the angle is. And like if you shoot it straight up, it's hardly going to go anywhere at all. So we've got 2 cases to think about. The simplest case, where we're just firing things off at a perfect horizontal angle to the ground. And in that case, all we need to know is how fast is it going and how high up above the ground does it start. And then we have the more complicated case where all of a sudden we have to start adjusting angles. And we're going to look at both of those down the road. And we're not going to look at any of it today. We'll start with this on Thursday. But ultimately, what we'll need to be able to do is predict for both horizontal and angled launches. So we'll work through this on Thursday. And then the last thing that I want to do is just review a couple of things that sometimes get confusing before you get started. So we often, and probably in math you've done this dozens of times, we often draw arrows and say this is a vector. And that's not true. Arrows and vectors are two different things. A vector is a quantity, oops, I have to do this the right way, is a quantity with magnitude, which means size and direction. It doesn't have a start and an end, and it is not located anywhere in space. It just has a size and a direction. That's it. An arrow is a physical drawing or a physical object. And that arrow, so arrows are physical objects or drawings. We are going to use them a lot to represent vectors. They can represent vectors the length of the arrow tells us about the magnitude and the direction of the arrow indicates the vector direction. But arrows aren't vectors, and vectors aren't arrows. We're going to use arrows to represent vectors. And what gets confusing about it is that we're going to use arrows to represent different kinds of vectors: displacement vectors, velocity vectors, acceleration vectors, force vectors, momentum vectors. All of those quantities have a magnitude and a direction. We're going to represent them with arrows. We're going to do mathematical stuff to the arrows, but arrows aren't vectors, which means we can't take an arrow that represents a force vector and combine it with an arrow that represents a displacement vector. We can put those two arrows together and we can do some math with them, but we'll get garbage if we do that because they aren't actually the same kind of quantity. That's where it gets confusing, because we're going to use arrows to represent different types of quantities. They're all going to look the same on paper. Yeah.
Is there any way to give position to the vector? Like you were talking about like a rocket ship, like getting closer.
No. So position itself is a vector quantity, but it doesn't have a position, if that makes sense. What a position vector tells you is how far away a point is from an arbitrary location that we call position 0, and it tells us what direction that point is in. That's it. So it tells us a distance, essentially. But a velocity vector is not located in space. We can draw an arrow and we can put it on a piece of paper, but objects don't have a velocity that is located somewhere. The object has a position, but its velocity vector doesn't. And that gets confusing because we're going to draw pictures and we're going to draw velocity vectors on those pictures, and it's going to look to us like those are arrows that are located in space. They're not. So part of the work that you're going to do today and going into our next class period is going to be to play around with that. So there is an assignment on Canvas. And that assignment is called the vector simulation activity. And I want you to just get started with this. You'll play around with it. We'll get into the math stuff next class, but for today, just get started with this. The only thing I need to tell you is this symbol, capital R, is a generic symbol for a vector. So you're going to be working with three vectors. One is vector A, one is vector B, one is vector C. You'll see, instead of an R, you're going to see an A or a B or a C. So when I say R, I mean for any one of those three vectors, either A or B or C or all three, all right? So play around with it. My guess is that you'll be able to get through at least part 5 of this. You should do it do it neatly, show me what you can actually do. Remember what we talked about earlier in the week? Here's my example. I did this assignment myself last year, and this is what it looked like when I did it. So I did it on graph paper because it's a lot easier to draw vector quantities on graph paper. And I did it neatly and cleanly. Anybody could look at this and follow it. That should be your goal as well. Not because of the points, but because that's the best way to think about and learn and understand this stuff. All right, you have the rest of the period to work on this, and we'll pick up from here on Thursday.
Mr.